All right, so continuing with solubility, right? Let's now say that we dissolve a salt in a solution of water and one of the common ions in the salt. In other words, we're making an aqueous solution that contains one of the ions in the salt, and then we are going to try to dissolve the salt into that solution. Okay? So, for example, right, let's try to dissolve silver chromate, Ag2CrO4 solid, in a solution of water and silver nitrate. Notice that this solution is made up of water and a salt that contains a common ion, or an ion that is the same as one of the ions in our salt. Okay, notice that silver will appear. Now, silver nitrate is fully soluble, so it will completely dissolve, right? Which means we will have silver ions in the solution that we're trying to dissolve our silver chromate in. Okay, so right, we know that AgNO3 completely dissolves, right? So H2O, Ag plus, and NO3 minus. Okay. All right. Now, this addition will lower our solubility of the Ag2CrO4. Okay, so this will lower our solubility. Why? Right? Well, let's consider our equilibrium. Right? We know that we have Ag2CrO4 solid, right? And we're going to be adding that, right, into water, and part of it will dissolve and will establish an equilibrium with 2Ag plus and CrO4 2 minus. Okay? If we add more Ag plus into solution, right, that would be like increasing that side, right, which will push our equilibrium to the left. When we're pushing our equilibrium to the left, that means that it prefers even more to be a solid. Okay? So that pushes to the left. Right? And that will lower our solubility. Okay? So let's see how this affects our KSP, or our solubility product constant, right? Because that's going to be dictating our equilibrium, right? So on slide 7 now, right? Let's see how KSP is affected by those common ions. All right, so the example on slide 7 is that cerium iodate, so CeIO3 in a 0.20 molar potassium iodate solution. So the cerium iodate has a solubility. See if I can write that a little bit more neatly. Has a solubility of 4.4 times 10 to the negative 8, right? What is the KSP? All right, well, we look at our solution, right? We know that it's going to be a solubility problem. Right? And if it's a solubility problem, we're always going to start with an ice table, right? Because we know if it's a solubility problem, then it's an equilibrium problem, which is dictated, of course, by that KSP, or well, by the KSP that we're trying to solve, right? So, we're setting up an ice table, right? So, step 1, let's write our ice, which is going to be CeIO3 solid. We're going to throw that into water. Again, we're leaving out our water because that column would just go away. Okay, and that dissociates and forms an equilibrium with Ce3 plus aqueous plus 3 iodate ions that are also aqueous. Okay? All right, now within that table, right, we know that we're going to have no solids. Okay, so this column goes away. All right, now B is going to be a little bit different, right, because we have common ions. So here we need to ask ourselves, do we have common ions? All right, the answer is yes, right, because our common ion, we have 3 iodate, right, but we're also going to be adding potassium iodate into that solution, right? So our common ion that's shared between those two species is our iodate, right? So iO3 minus, okay? So if we have a common ion, then that means we need to figure out what its initial concentration is in our solution, okay? Now, we have 0.2 molar, right? So that's moles per liter. Moles of potassium iodate per liter of solution, right? And for every 1 mole of potassium iodate that we add, we are going to get 1 mole of iodate ion in solution. Okay, so that means that our initial concentration of iodate ion is going to be 0.2 molar. Okay. And we haven't added any of our cerium yet, right? Because this hasn't dissolved any yet. Okay, so there's going to be 0. All right, and we're going to finish out our table, right? So step C would be to finish the table. Okay, we should all know how to do this by now, right? We have 1 times plus 1, or sorry, 1 times plus x, right? And then here, right, because we had 1 in front of that, here it's going to be 3, right, from our stoichiometry, times a positive x, right? They're positive because they're on the right side of our double arrow, right? They are going to be our products, right? So we have an x, and we have a 3x. Oh, I'm sorry, not quite, right? We have a 0.2 plus 3x, right? Let's not forget about our common ion that we've added, okay? Get rid of this. All right. So we've got steps A, B, and C for our table, right? So now, step 2, right? Step 2 is going to be our KSP expression. Okay, so KSP for this process is going to equal our cerium 3 plus, right, to the first, and our iodate ion to the third, okay? And I recommend writing these out every time because we're going to have to incorporate our stoichiometry as our exponent as well as our equilibrium components, okay? So then we're going to evaluate, right? And we're going to see that we have x times 0.2 plus 3x to the third, okay? I would not recommend taking any shortcuts in this process, okay? That's where you'll end up making a lot of mistakes if you're not too careful. All right, so the third step is going to be to use that extra info, right? We know that we have a solubility, right? So use extra info, right? We know that our solubility, right? Our solubility is going to be our concentration of our solid, right? So our cerium iodate at equilibrium, right? Which corresponds to 4.4 times 10 to the negative 8, right? And that's going to be moles per liter, okay? So now what I want to do is I want to convert it into cerium. Why would I want to convert it into cerium? Because it's going to be the one that corresponds directly to X. And if I can get X, then I can plug it into that expression and get my KSP. All right, so we know that this is moles of the cerium, right? So 4.4 times 10 to the negative 8 moles of cerium iodate per liter. And for every 1 mole of cerium iodate, I'm going to get 1 mole of cerium 3 plus, okay? Which means that my concentration of cerium 3 plus at equilibrium is equal to 4.4 times 10 to the negative 8 molar, okay? Now, that also corresponds to X. I can then plug in my X for KSP. So KSP into my KSP expression, right? So I have 4.4 times 10 to the negative 8 times 0.2 plus 3 times 0.0. So 4.4 times 10 to the negative 8 times 0.2 plus 3 times 4.4 times 10 to the negative 8. All right, and all of that gets cubed, okay, and that will end up giving you a K equal to 3.5 times 10 to the negative 10. All right, so that would be how we find our KSP using our solubility into a common ion solution, okay? Now, what if we wanted to go the other way? What if we had our KSP and wanted to find our solubility in a common ion solution? Right, well, that would be our next problem. Okay. So, slide 8, this will be, right, to find our, so what is the solubility of silver 2 chromate, CrO4, okay, that has a KSP equal to 9.0 times 10 to the negative 12. What's the solubility in water? And the solubility in a 0.100 molar solution or aqueous solution of silver nitrate. Okay, so since this is going to be another one of those equilibrium problems, how are we going to work through this? What's our first step going to be? Let's do this for the water, right? So for our water, right, very first thing we're going to do, set up an ice table, right? We know it's an equilibrium problem, okay? So we have Ag2CrO4, throw that into some water, and we get 2Ag plus CrO4 2 minus, okay? ICE. Again, there are going to be no solids, so we can quickly eliminate that, right? Do we have any common ions in just pure water? No, there are none, right? So right off the bat, we know that these concentrations are both going to be 0, okay? Then we fill out the table just like we always do, right? 2 from our stoichiometry times plus x, 1 from our stoichiometry times plus x. We have x, we have 2x, right? Our next step, as always, is going to be to write our KSP expression, okay? And our KSP expression, our solubility product constant, is going to be equal to concentration of Ag plus squared times our concentration in CrO4 2 minus, okay? Which in this case is going to be 2x squared times x, which is equal to 4x cubed, okay? We have the KSP, okay? So our KSP, right, is equal to 9.0 times 10 to the negative 12, okay? Which means that it's relatively easy. Sorry. Goodness. All right. Which means that we can now solve for our x, okay? Our x in this case, right, we would divide by 4 and take the cube root of it. It's going to give us an x equals 1.31 times 10 to the negative 4th, okay? Now, which of these ions does that correspond to? Corresponds to our concentration of CrO4 2 minus at equilibrium, okay? Now, that has a 1-to-1 relationship with our solid. Again, at this point, we're trying to get back to our concentration of solid because that will be our solubility, okay? So this corresponds 1-to-1 to our solid, right? So this is AgCrO4. Again, that comes from the fact that if we know how much of this we had in solution, that's going to be how much of that dissolved, okay? Or rather dissociated into ions, okay? So that would mean that 1.31 times 10 to the negative 4th is our solubility. Oh, and don't forget your units. It should be molar, okay? All right, now what about our other case where we put it into a solution of silver nitrate? All right, well, we know it's going to be an ice table. Okay, so we have Ag2CrO4, throw that into water. It will form an equilibrium of 2Ag plus CrO4 2 minus, ICE. We know that we are going to take out our solids, right? Now, the next step, so A would have been no solids. Part B, right, would have been, did we have a common ion? Okay, and so we have silver nitrate and we have silver chromate, right? That means that our common ion is going to be silver, right? It's shared between our aqueous solution and the salt that we're trying to dissociate, okay? So we have silver, Okay, so that means that we're going to need to figure out our initial concentration of silver, right? There's going to be none of our chromate, right? Because there's no silver or there's no silver chromate, there's no chromate in our solution yet. Okay, so now we will take 0.100 molar silver nitrate, right? We know that molarity is moles per liter, and we'll convert this into silver, right? So that would be 1 mole silver nitrate to 1 mole silver plus, because it completely dissociates. Remember, all nitrate salts are soluble. So we will have 0.100 molar as our initial concentration. 100 molar Ag plus. Okay. Now we fill out the table as always. So using stoichiometry, that's 2 times plus x, 1 times plus x, leaving us with x and 0.1 plus 2x. Okay. Okay. And then in part 2, right, and I'm going to erase that part. We know that C was to finish the table. Part 2 is to set up our KSP expression, right? So that's going to be x times 0.1 plus 2x squared. Okay, remember I got that by taking my concentration of CrO4 minus to the first, right? And my concentration of Ag plus to the second. Okay? Now I know what my KSP is. That's equal to 9.0 times 10 to the negative 12. Okay? But if I go through all of this and multiply everything out, it's going to give me an x to the third. Now, last time I checked, y'all didn't know really convenient ways of getting that x out of an x to the third. So what I'm going to suggest is that we make a little bit of an approximation, okay, where we drop that 2x portion. All right, so we're going to approximately say that that is 0, okay, which means that we'll have to do a 5% sort of rule check, right? But I'm going to skip that for the sake of time and just say, okay, so now I have x, right, times 0.1. I've dropped the x. I have x times 0.1, right? I've dropped the plus 2x, and that's still squared, okay? That's going to be equal to my 9.0 times 10 to the negative 12, okay? All I've done here is say that that 2x was approximately 0, which is going to simplify that equation, okay? Now, I simply divide by 0.01, right, or 0.1 squared. So then 9.0 times 10 to the negative 12 divided by 0.1 squared. That's equal to 9.0 times 10 to the negative 10th. Okay? Before I box that, right? Let's think about this for a second. We know that the X corresponds to the chromate, CrO4 minus, at equilibrium, which is how much of that dissociated, right? Because it's a 1-to-1 ratio, which means that this also happens to be my concentration of my Ag2CrO4 at equilibrium that dissociated, which means that that is my solubility. Okay, now notice that this is 10 to the minus 10th, that was 10 to the minus 4th. Okay, so that means that when we didn't have the common ion in solution, right? That was for our pure water example. When we didn't have a common ion in solution, it was much more soluble. we could dissolve and dissociate much more of the silver chromate when there wasn't the common ion, okay? And again, that's because if we've added any of our common ion into solution, okay, then that means it's going to push our equilibrium back to the solid state, all right? And with that, that will conclude today's lectures, and I will see you all on Wednesday.